Hello. Hello. Good afternoon, students.
Good afternoon, sir.
Okay. Okay. Hmm. Uh, Today's class, we are going to discuss about torsion of circular shafts. Okay. Before going to discuss about torsion of circular shafts, first please understand what is meant by the shaft here. Then we will discuss about what is meant by the torsion. First, please understand what is meant by the shaft, why the shaft is subjected to torsion. Okay. Yes. Please look at this. It is a member which is subjected to twisting moment or torque. Okay, it is a member which is subjected to twisting moment or torque. Okay, then that kind of member we are calling as a shaft. Okay, in the first class, I told that while designing the member, first we have to identify the member. While designing the member, first we have to identify the member. Okay, the member, it may be the bar or beam or shaft or frame or column or truss, whatever it may be the member. First we have to identify. How to identify the member? What I said earlier. Okay, the member we are calling as a shaft, we are calling as a beam, we are calling as a bar. It is only depends upon okay, direction of load here. What kind of load acting on the member? That is a very important. Okay, the bar means the member which is subjected to axial load. Beam means the member which is subjected to transverse load. In the same way, okay, the shaft means the member which is subjected to the twisting moment. The member which is subjected to the twisting moment here. Generally, we know there is a two kinds of moments. One is the bending moment, second one is the twisting moment. The beam is subjected to the bending moment, but the shaft is subjected to twisting moment here. Okay, the beam is subjected to the bending moment, the shaft is subjected to the twisting moment. This twisting moment is also called as a torque here. We know that generally moment is nothing but force into perpendicular distance. Okay, moment is nothing but force into perpendicular distance here. That kind of moment we are calling as a twisting moment. Yes. Yes. And the next point, okay, where we are using the shafts here. Why we are going to use the shafts in a particular place here? Yes, the shafts are used to transmit the power from one place to another place. Suppose, for example, if you want to transmit the power from one place to another place, we know that. Okay, we can look at the rice mills or flour mills in so many industries also. Okay, we can transmit the power from origin to the different places. Okay, from origin to the different places. How we can transmit the power is nothing but just we can rotation, we can transmit the rotation motion, rotary motion, or okay, translatory motion. That means you can transmit the motion. Power means motion. In the mechanically, the power means motion. The shaft is used to transmit the power from one place to other place here. And the next sentence, while transmitting the power, the shaft is subjected to the twisting moment due to the rotation. Okay, when the shaft is rotating, it is subjected to the twisting moment. And bending moment due to the self weight of pulley or gear here. Bending moment due to the self weight or pulley or gear here. Just we can look at this diagram here. Okay, you can understand. Okay, this is the motor. Okay, we can purchase the one motor. Let us assume that 5 HP motor we purchased. Okay, we purchase the 5 HP motor and it is placed in the rice mills here in a particular place. Okay, from that we can transmit the power from so many okay places here. How we can transmit the power? Okay, in the rotor there is a one shaft is there. Okay, in the rotor there is a one shaft is it is rotating with a particular speed here, and that shaft is connected to the another shaft here. That shaft is connected to the another shaft here by means of coupling here. This is called as a coupling. By means of coupling we can connect. Okay, now when the shaft is rotating, the shaft which is placed in the motor, it is rotating, then the shaft is also rotating here. Technically the shaft is called as a okay driver shaft here. The shaft is called as a driver shaft here, and the shaft is called as a driven shaft here. Now the driver shaft is rotating here. Driver shaft is rotating. When this driver shaft is rotating, on the driver shaft we are placing the pulley. On the driver shaft we are placing the pulley here. Then pulley is also rotating here. Now this motion or power is transmitted to the another place. So suppose I want to transmit the power from this place to the this place here, then we can place the one more shaft at a particular place here. On the shaft also we can place the one more pulley here. These two pulleys are connected by means of belt. These two pulleys are connected by means of belt here. This is the belt. Okay, by means of belt here. When this driver pulley is rotating, driven pulley is rotating. When the driven pulley is rotating, the shaft is also driven shaft is also rotating. Okay, that is the power is transmitted from one place to the other place here. Okay, from one place to the another place here. First, the power is transmitted from the shaft which is placed in the motor to the driver shaft here, driver shaft to the pulley, pulley to the driven shaft here, driven shaft to the driven pulley to the driven shaft. Like that, we can transmit the power from one place to other place here. We can observe here. Okay, now while transmitting the power, okay, the shaft is rotating. How the shaft is rotating? On the shaft, we can apply the tangential force. On the shaft, we can apply the tangential force. That tangential force multiply with radius, okay, which is called as a twisting moment. If you are applying the tangential force, it is try to rotate. Okay, that tangential force multiply with radius, it is called as a twisting moment here. That is the meaning of that one. While transmitting the power, we can look at this sentence. While transmitting the power, the shaft is subjected to the twisting moment due to the rotation and bending moment due to the self weight of pulley. Now, okay, we can look at here. This is called as a pulley. Pulley has some self weight here. That self weight is acting as a transverse load on the shaft. That self weight is acting as a transverse load on the shaft here. Okay, we know due to the transverse load here, okay, due to the transverse load, the shaft is subjected to the bending moment or not here. That is the meaning of that sentence. Bending moment due to the self weight of the pulley or gear. One more important point. Okay, there is a different types of mechanical drives are there. Okay, there is a different types of gear drive system is there, belt drive system is there, and chain drive system is there, and rope drive system is there. There is a different kinds of okay, mechanical drives are there. This is the belt drive. This is the belt drive here, and sometimes there is a chain drive is there. Now, suppose for example, instead of belt here, there is a chain, but instead of pulley, okay, there is a sprockets are there. Let us see in the bicycles or motorcycles. Okay, generally we are using the okay chain drives here. Okay, then the self weight of this sprocket, okay, is acting as a transverse load here. And the gear drive, we are very familiar with gear drive here. The self weight of the gear is acting as a transverse load here. Like that, there is a mechanical drives are there. Okay, any mechanical drive, okay, to transmit the power by using any mechanical drive, the self weight of the pulley or gear or sprocket, okay, it is acting as a transverse load. Due to the transverse load, okay, the shaft is subjected to bending moment. But whereas in this torsion of circular shafts here, that bending moment is neglected. We are not considering that. We can ignore that. But we know that how to find out the bending moment. We can find out the bending moment like that. We can find out the twisting moment like this here. Okay, from the twisting moment, there is a shear stresses will be developed here. Due to the bending moment, bending stresses will be developed here. Thereafter, we can look at here how to calculate the total stress or resultant stress. That is the okay. Next topic we will discuss about here when the two stresses are acting at a point here. How to calculate the total stress we will discuss in the principal stresses and strains topic. Okay. Is it clear, students? Hello.
Yes, sir. Yes, sir.
Could understand why the shaft is subjected to the twisting moment and why the shaft is subjected to the bending moment? Okay. And next one, pure torsion. In the bending stresses, we already discussed about pure bending. In the same manner, we will discuss about pure torsion. What does it mean is, the shaft is said to be under pure torsion when it is subjected to two equal and opposite twisting moments or twisting couples. Two equal and opposite twisting moment or twisting couple. Let us consider the one shaft is like this here. Okay, let us consider the one shaft is like this, which is subjected to the twisting moment T. Twisting moment is also called as a torque here, twisting moment T, in a clockwise direction. Suppose, for example, it is subjected to the clockwise direction at the free end of the shaft here. Then what kind of direction is there at the support here? Already I told that, okay, opposite to the direction of the load, na reaction. At the support, there is a reaction will be developed here. That is always opposite to the, okay, external load here. Okay, then it okay, free at the free end there is a clockwise moment, and at the fixed end here there is an anti-clockwise moment here. Now we can look at here, the shaft is subjected to two equally and opposite okay, twisting couples are not, or twisting moment are not, then okay, this shaft is said to be under pure torsion. That is the meaning of pure torsion. That means pure torsion means only the shaft is subjected to the twisting moment. Okay, it is free from bending moment. There is no bending moment. That means there is no self weight is acting on that. Generally we may get a doubt here, sir. Generally to transmit the power, okay, on the shaft we are placing the pulley or gear or like this here. If you are placing like this, then it is not called as a pure torsion. Okay, we can find out the okay stresses only due to the twisting moment here. Okay, already we know that how to find out the stresses due to the bending moment. Already we know that how to find out the stresses due to the bending moment. Okay, then I will discuss how to find out the stresses due to the twisting moment and bending moment. Yes, next sentence. When the shaft is subjected to the pure torsion, the twisting moment is constant. Yes, here how much twisting moment is there? T. Here also T, at here also T. From right end to the left end, we can look at it anywhere. Okay, the twisting moment is constant and bending moment is zero. Already I said that okay, it is free from the bending moment, then the bending moment is zero. Okay, that is about okay, what is meant by the pure torsion? Okay, pure torsion. Next one, torsion equation. It is a very important equation. The total torsion of circular shaft unit, it is depends upon this equation only. Like a bending stress unit, it is depends upon the bending equation. Okay, like this here also it is only depends upon the torsion equation. Okay, now this equation we are getting from the derivation. Okay, I am not going to discuss about the derivation here. Just I wrote the equation. T by J is equal to tau by R is equal to G theta divided by L here. G theta divided by L. This equation look like a bending equation. Okay, now first I am going to discuss about each and every term in this torsion equation here. Please remember, very important. Okay, T by J is equal to tau by R is equal to G theta divided by L. Okay, first we can look at here. I am going to explain each and every term. Now, first one is the T is equal to maximum twisting moment or torque, or it is also called as a resisting torque here. Maximum twisting moment or torque, it is also called as a resisting torque here. Now, okay, how to find out this one? Already I told that okay, there is some amount of tangential force is acting on that shaft here. That tangential force multiply with radius. Radius is nothing but perpendicular distance. Multiply with radius, then it is called as a okay twisting moment. Here we can find out the twisting moment like this. Sometimes the tangential force is given and radius is given, like that we can find out the T. Now we know that this is subjected to the torque T here. Yes, one thing you remember, please look at this diagram. Okay, yes, we can look at this diagram here. This diagram, please look at this diagram. In this diagram, okay, this is the axis of the shaft. First I am going to discuss about the dimensions here. This is the axis of the shaft, and this is the length of the shaft and radius of the shaft R here. Length of the shaft L and radius of the shaft is L here. Okay, now I am going to considering the one line. Please look at this line. I am going to consider the one line here. This line is parallel to the axis of the shaft. That line is parallel to the axis of the shaft. When that line is parallel to the axis of the shaft here, that shaft is not subjected to twisting moment, then that line is parallel to the axis of the shaft. When it is subjected to the twisting moment, then we look at here, I am considering this is the AB line. Now this AB line becomes a B dash line here. That means B moves to B dash. Now B moves to B dash here. Now we can look at here, this is the line, B moves to B dash. Okay, why the B moves to the B dash? Due to the twisting moment. Due to the twisting moment. That means when the B moves to the B dash, it is made by some angle that is called as a pi here. Generally, most of the students, they can answer what is meant by this angle. This angle is called as the angle of twist. No, it is not called as the angle of twist. It is called as a shear strain. It is not called as an angle of twist. Okay, most of the students, they do the mistake here. It is the shear strain, it is not angle of twist here. Okay, that is called as a pi here. Okay, that is called as a pi here. And next one, okay, this is the center of the shaft here. Okay, this is the center of the shaft here. Okay, from the center of the shaft, we can draw the one line to the B, we can draw the another line to the B dash here. These two lines make an angle, some angle which is called as the angle of twist. Okay, that is the angle of twist. It is not angle of twist here. Okay, it is not angle of twist. Okay, we can observe here. What is the difference? Generally, we may get a one doubt here. Sir, can you answer what is the difference between angle of twist and shear strain? Yes, we can observe from this diagram. The shear strain is independent on length. Yes, it is independent on length here. Okay, whereas in the angle of twist, it is depends on length here. If the length is changes, then angle of twist theta is also changes here. The next one, you can look at here this angle of twist theta. Okay, it is independent on radius. It is independent on radius. Okay, at the center, the angle is theta. Okay, at a distance of 5 centimeters theta, 10 centimeters theta, at the free surface also it is theta. But it is okay, depends on length here. It is depends on length. Now finally I conclude. Shear strain is independent on length of the shaft but depends on radius of the shaft. Whereas in the angle of twist is independent on radius of the shaft but it is depends on length of the shaft here. Okay, now already I mentioned that sentence also here. Look at this one. Yes, angle of twist theta depends on length of the shaft but independent on radius of the shaft. Shear strain is depends on radius of the shaft here. Okay, but it independent on length of the shaft here. Okay, length of the shaft here. That point you have to remember. That point we have to remember. Okay, now that is the okay diagram. Okay, next one, J, where J is equal to polar moment of inertia. Yes, it is called as a different names here. Okay, polar moment of inertia. It is also called as a okay moment of inertia about okay z axis. Sometimes it is also called as a moment of inertia about axis of rotation also. Moment of inertia about axis of rotation also. We are also calling as a like that. Yes, but we may get a doubt here, sir. Whereas in the bending equation, m by I is equal to f by y is equal to e by r, where I is equal to moment of inertia about x-axis. Moment of inertia about x-axis. But why should we consider the moment of inertia about z-axis? Just we can look at here. We are applying the angle of, sorry, we are applying the twisting moment about z-axis. Okay, we can look at here. This is the axis of rotation. That axis of rotation is a, suppose for example, I am going to draw the one line here. Okay, this is called as the x-axis. And I am going to draw the another line here. Okay, this is called as a y-axis here. But okay, exactly perpendicular to this x-axis and y-axis, there is a one more axis is there, that is called as a z-axis. Okay, okay, that is called as a z-axis. Just we can observe here the twisting moment okay acting about the z-axis. That's why we should considering okay axis of sorry, we should considering the moment of inertia about z-axis. Okay, that is also called as the axis of rotation. Okay, technically it is called as a polar moment of inertia. Okay, technically it is called as a polar moment of inertia here. Okay. Okay. Now we know how to find out that polar moment of inertia. How to find out that polar moment of inertia? I think we studied in the engineering mechanics. Izz is equal to Ixx plus Iyy. Izz is equal to Ixx plus Iyy here. Okay. Now for solid shaft, Ixx is equal to pi by 64 d power 4 plus Iyy also pi by 64 d power 4, which is equal to pi by 32. Okay, d power 4 here, pi by 32 d power 4. And for hollow shaft, okay, Ixx is equal to pi by 64 capital D power 4 minus small d power 4 plus pi by 64 capital D power 4 minus small d power 4 here, which is equal to pi by 32 capital D power 4 minus small d power 4. Like that we can find out okay, J for solid and J for hollow, okay, where small d is equal to inner diameter and capital D is equal to outer diameter. Okay, capital D is equal to outer diameter here. Okay, now the next term is tau. Tau is equal to maximum shear stress or the shear stress at the outer surface of the shaft here. Generally students answer where tau is equal to shear stress. Already I told that on a cross section, okay, any kind of stress, it is not constant. It varies from point to the point except axial stress. Except axial stress, remaining any stress, is it bending stress, shear stress due to the twisting moment, shear stress due to the okay shear force, any kind of stress, it varies. Okay, that's why, okay, while answer what is meant by the tau, please answer. Okay, it is a maximum shear stress. Don't call it a shear stress. Shear stress is not constant. It is constant, then we are calling as a shear stress. It is not constant. The shear stress at the okay outer surface of the shaft here. Outer surface of the shaft means here. This is the meaning of outer surface. Okay, the shear set the shear stress at the center is different, at a particular radius is different. If the radius is increases, then the shear stress is also increases here. Okay, the maximum radius is there at the outer the maximum radius is there at outside of the shaft here, then the shear stress is also maximum. Okay, that's why I am calling as a tau is equal to maximum shear stress here. Next one, r is equal to radius of the shaft here. Okay, r is equal to radius of the shaft. Next one, theta is equal to angle of twist in radians. Don't take the in terms of what you call angle here, please, in terms of radians here, not a sorry, in terms of degrees. Don't take in terms of degrees, please, in terms of radians here. We know that okay, 1 radian is equal to 180 degrees na. Okay, pi, that relation already you know that. Okay, next one, pi is equal to shear strain in the radians here. Now L is equal to length of the shaft. L is equal to length of the shaft. Already explained about this one. Okay, already explained about this one here. This is about terminology we are using in the okay torsion equation. Hello students,
Sir.
could understand the terminology?
Yes, sir.
First of all, could understand what is meant by the shear strain and what is meant by the angle of twist? Shear strain and angle of twist. Hello.
Yes, sir.
Okay. Okay, thank you. And next one, analysis of torsion equation. Previously, just we discussed about the terms used in the torsion equation. Now, how the torsion equation is applied for the shaft here? Just we can look at here. T by J is equal to tau by R is equal to G theta divided by L here. Just I am considering T by J ratio is A and tau by R ratio is B and G theta divided by L ratio is C here. This is C here. Now here case 1. Now already I told that to design the any member, we are going to consider the some criteria here. The first is the strength criteria, second one is the stiffness criteria. First I am going to consider the strength criteria. In the strength criteria, we are going to calculate the stress. Now we are going to look at how to calculate the stress here. How to calculate the stress here. Case 1 strength criteria. In the strength criteria, only we are going to discuss about the stresses only, that to shear stresses, how the shear stress is varies here, how to calculate the shear stress here. Shear stress here. How to calculate the okay shear stress here. Yes. Now to calculate the okay shear stresses, okay, first considering the AI is equal to B, that means T by J is equal to tau by R. T by J is equal to tau by R. From this, can I write like this here? Tau is equal to T by J into R. Tau is equal
Yes,
to
sir.
okay T by J into R. Yes, for a given cross section, okay, T and J are constant. Yes, okay, the T and J are is constant for a given cross section. Okay, what does it mean is, what is the meaning of this sentence is, yes, we can look at this one. Suppose for example, we can look at this one. I select the one cross section. Which cross section we can select here? the maximum twisting moment is acting on a particular cross section, we can take that one, like a maximum bending moment, like a maximum shear force. Here also we can select that one here, we can select that one here. On that cross section, okay, the twisting moment is constant. The twisting moment, it may changes, okay, plane to the plane, cross section to the cross section, but on the cross section which are selected already, on that cross section it does not vary. Suppose for example, here is okay, one j value, sorry, t value, here is another t value, here is another t value, okay, here is another t value, not like that. At anywhere that t is constant here, in the same fashion j is also constant here, but r is not constant, brother. What is the value of the r at the center? 0. Now the r values goes on increases, r is maximum at the outermost layer here, that means okay, surface of the shaft here. That is the meaning of this sentence. For a given cross section, t and j are constants, and okay, that means tau is directly proportional to the r here. Now, okay, from this equation, from this relation, we establish the, okay, sorry, we can draw the shear stress distribution diagrams here. First, we can look at here. That means the shear stress is directly proportional to the radius, and the shear stress varies linearly. How it varies linearly? What I said earlier. Okay, if the variable power is 1, varies linearly, power is 2 parabolically, power is 3 cubically, like that. Okay, the power is variable power is 1 here, that's why it varies okay, linearly, and also it is directly proportional. Suppose for example, the radius is 0. If the radius is 0, then the shear stress is also 0. If the radius is maximum, then the shear stress is also maximum here, maximum. Okay, just we can look at this diagram here. The shear stress is 0 at the center. Okay, from this one, the shear stress, that shear stress is goes on increases. The shear stress is goes on increases. It is maximum at the surface of the shaft. In the same fashion, okay, here also it is maximum at the, okay, surface of the shaft here. It is maximum. It is maximum at the surface of the shaft here. But we can look at here this diagram, it is look like a bending stress distribution diagram. Exactly, no doubt in at all. This diagram, it is look like a bending stress distribution diagram. Okay, don't confuse the shear stress distribution diagram due to the shear force. The shear stress distribution diagram due to the twisting moment is different. We know that the shear stress due to the shear force, okay, it is maximum at the center, but here 0 at the center, and okay, it is 0 at the outermost layer, but it is maximum at the outermost layer, and that is that shear stress distribution diagram. The shear stress varies parabolically like this. It varies like this here parabolically, but it varies linearly. That thing you have to remember. The shear stress due to the shear force and the shear stress due to the twisting moment, both are different. Okay, both are different here. Both are different here. Okay, next one, in the same manner. Okay, this is for solid shaft, this is for hollow shaft here. This is for solid shaft and this is for a hollow shaft here. In the same manner like this, it varies linearly, maximum at the surface of the shaft. But one thing you remember, in this region, there is no shear stress. Yes, there is no shear stress. Why? There is no material. Is there any material at here? There is no material. Okay, okay, without material, how the load can resist? Okay, there is no resistance. If the resistance is not there, okay, then the stress is not developed. Okay, the stress is only developed due to the resistance. If the resistance is not there, then the stress is not developed here. That's why in this region there is no, okay, stresses here. Finally, I conclude. Okay, this value is there, tau max. Okay, you can find out the this tau max value by using the formula. I will discuss later. That value compare with the shear strength of the material. If that value is less than the shear strength of the material, then the shaft is safe. Okay, otherwise the shaft is failure here. That's why the stress is always less than the strength of the material. Students could understand this. Hello.
Yes, sir.
Could understand this?
Yes, sir.
How the shear stress is vary so over a shaft. Okay. Why the T and J are constants? Hello.
Reading.
Okay. Okay. And next one. Okay. Now the same equation we are using to calculate the shear stress. Same equation we are using to calculate the shear stress here. Okay, T by J is equal to tau by R. Tau is equal to T by J into R here. T by J into R here. That means T is equal to T by J by R here. T by J by R here, where this J by R is called as a ZP. I think in the bending stress diagram also, sorry, bending stress topic also. Okay, F is equal to M divided by, okay, M divided by, I think instead of J, I by Y, where I by Y is called as a Z. Na? In the same fashion, here J by R is called as a ZP, where Z already we discussed here, where Z is called as a, okay, section modulus. But whereas in shafts it is not called as a section modulus, it is called as a polar section modulus. That P, ZP means polar section modulus. Just we can look at here polar section modulus in mm cube, because J in terms of mm power 4, R in terms of mm get cancelled, which is equal to mm cube here. Then ZP is equal to J by R. ZP is equal to J by R. ZP signifies the strength of the cross section in twisting. Okay, already I said that in the bending equation, Z signifies the strength of the cross section in bending. Which cross section is the best one? That is depends upon the Z value. Which cross section has maximum value of the Z? That is the best cross section. Already we compare the I section, okay, rectangular cross section, circular cross section, and square cross section like that. Here also, which cross section is the best cross section? That is depends upon the ZP value, which gives the maximum value of ZP. That is the best cross section. But one thing you remember, okay, this is the very important thing here. Here we can't ZP value, we can't compare with the different cross sections here. Only we can compare with the circular cross sections only, because R is only valid for circular cross sections where R is equal to radius. That means the torsion equation is also valued for circular shaft, either solid circular or hollow circular. Either solid circular or hollow circular. It is valid for okay, circular shafts only. That's why if you want to compare, only we can compare the solid and hollow. In this solid and hollow, which is the best one? Okay, which is the best one? Don't compare with the I section or rectangular cross section, square cross section. In the square cross section, what is meant by the R? Okay, we can't define what is meant by the R in a okay, square cross section or rectangular. Okay, that means non-circular cross sections, this equation is not valued. This procedure is also okay, not valued to calculate the shear stresses for non-circular shafts here. That's why we can look at the topic name is torsion of circular shafts. Okay. But we may get a doubt here, sir. The shafts are always in a circular cross section. No, it is in a rectangular cross section also. It is in a trapezoidal cross section also. In such a case, sir, how to find out the stresses? We may get a doubt here, sir. In such a case, how to find out the stresses? Okay, non-circular shafts here, but that is a different procedure to calculate the stresses here, shear stresses. But when you go to the MTech, we will discuss about that. Okay, here we are not discussing about that one here. It is not required. Only we are going to discussing about circular shafts only. Okay, for a given twisting moment, tau is directly proportional to, sorry, inversely proportional to ZP. If the ZP value is more, then the tau is less here. ZP value is less here, tau is more. What I said earlier also. As a design engineer, main objective of the design engineer is how to minimize the stresses. That is the very important. How to minimize the stresses here. If you maximize the ZP value, okay, then we can minimize the stress. Then we can minimize the stress here. That point you have to remember. That's why for best cross section, the ZP should be more. Okay, if the ZP should be more, then the shear stress should be minimum. Okay, yes, we can look at that sentence. For the best cross section, ZP should be more. We will discuss later. Okay, which one is the best cross section? Is it a solid circular or a hollow circular? We will discuss later that one also. Okay. Next one, how to find out the ZP value for solid shaft here? For solid shaft here, ZP is equal to J by R. Okay, J is equal to pi by 32 d power 4 already. Okay, we get this value previously. And radius is d by 2, which is equal to pi by 16 d cube. Very important formula, very useful formula in the problems here. ZP is equal to pi by 16 d cube. Please remember this. Please by heart this expression. ZP is equal to pi by 16 d cube for okay, solid shaft here. Next one, tau is equal to T divided by ZP. Okay, from that T divided by ZP value pi by 16 d cube, that is equal to 16 T divided by pi d cube. This is also very useful formula to calculate the shear stress here. Okay, we can calculate the shear stress like this in a solid shaft shear like this. In a solid shaft, after calculating this one, we can compare with the strength of the material. We can compare with the strength of the material here. Okay, that strength of the material is more than the stress, then the shaft is safe here, otherwise it is failure. Otherwise okay, it is a failure here. Okay, next one, for hollow shaft, ZP is equal to, for hollow shaft, ZP is equal to, okay, pi by 32 d power 4 minus small d power 4 divided by, okay, d by 2. Here we may get a doubt here, sir, which diameter we are going to consider, or which radius? J by R na, which radius? Please remember, outer radius we should consider. Outer radius we should consider. That's why I'm considering outer diameter divided by 2. Outer diameter. Okay. Then pi by 32 d power 4 is a common, capital D power 4. Then 1 minus small d divided by capital D whole power 4 divided by d by 2 here. And 2 and 13 are get cancelled here. D get cancelled. Pi by 16 d cube into 1 minus this small d divided by capital D. I am considering as a k. For sake of convenience, I am considering as a k here. Then k is equal to small d divided by capital D. Small d divided by capital D here. Okay, like that we can calculate the ZP, and that ZP value substitute in this expression, we will get 16 T divided by pi d cube into 1 minus k power 4. 16 T divided by pi d cube into 1 minus k power 4. Okay, this is the formula to calculate the shear stress in a hollow shaft. Okay, to calculate the shear stress in a hollow shaft here. Okay, brother, could understand this, students? Hello.
Yes, sir.
Yes, sir. Yes, sir.
Okay, what we discussed here, how to find out the shear stress in a shaft. Okay, this is the formula to calculate the shear stress in a shaft. This is for solid shaft, this formula for hollow shaft. Okay, this formula for hollow shaft here. Okay, and next one, okay, stiffness criteria. Stiffness. Next one is stiffness criteria. For stiffness criteria, please considering A is equal to C. A means T by J, C is nothing but G theta divided by L here. From this, theta is equal to TL divided by GJ. Okay, theta. Theta means angle of twist. It is the one kind of deformation. It is the one kind of deformation. If you observe, okay, in the bars, delta is equal to PL by AE. In the beams, WL cube divided by 3I. Okay, in the same fashion, okay, in the shafts, theta is equal to TL divided by GJ. Okay, TL divided by GJ. This is also very useful expression. Okay, please remember this one also. Theta is equal to G theta, sorry, TL divided by GJ. Okay, where GJ is called as a torsional rigidity. Torsional rigidity. Already I told that there is a three kinds of rigidity: axial rigidity, and flexural rigidity and torsional rigidity here, where GJ is called as a torsional rigidity in Newton mm square, because this is for Newton per mm square, and mm power 4 get cancelled, which is equal to Newton mm square here. Okay, next one, torsional stiffness. That is a torsional rigidity. It is a torsional stiffness. Okay, torsional stiffness here. It is a torsional stiffness here. please look at here. The amount of torque is required to cause the 1 radian of twist is called as a torsional stiffness here. Okay, that means we are applying the, if you are applying the, yes, we can look at this one, then we can understand very easily. Yes, this diagram, we can look at this diagram. If you are not applying the any torque on the shaft, then then we can look at here the lines, the planes are always parallel to the axis. That means I am considering as a AB plane. When it is subjected to the some amount of torque, then B moves to the B dash. That means there is some angle of twist is there. What I am saying is, if you get the 1 radian angle of twist, 1 radian means we know that in terms of angle pi by 180. Okay, 1 radian angle of twist. To get the 1 radian of angle of twist, how much torque is required? How much torque we can apply? Okay, that means we can apply the 5 kilonewton meter, we can apply the 10 kilonewton meter, we can apply the 20 kilonewton meter. How much torque we can apply to get the 1 angle of twist? 1 angle of twist means 1 radian of angle of twist. That is called as a stiffness. Suppose, for example, I am considering the more stiffer material for the shaft. Okay, that material is more stiffer. Then the amount of load is the amount of torque is required to get the angle of twist is more. That means the stiffness is always directly proportional to the load. Load means here twisting moment, and inversely proportional to the angle of twist. Suppose it is a more stiffer. Hello.
Sir. Sir.
Okay. Some disturbance is to it. Okay. Yes, that is the meaning of stiffness here. Okay, please understand what is meant by the stiffness. Yes, this one. The amount of torque is required to cause the 1 radian of twist. Twist means angle of twist, is called as a torsional stiffness. That is in the mathematically KT. K means stiffness, T means torsional, and K, this is equal to T by theta. Okay, it is equal to T by theta. T divided by theta means TL divided by GJ here. TT get cancelled. Then KT is equal to GJ divided by L. GJ divided by L here. Yes. Here, when you go to the interviewer asks the one question, very, very interesting question. Can you answer what is the difference between torsional rigidity and torsional stiffness? Generally, students say that, sir, torsional stiffness is the product of polar moment of inertia and modulus of rigidity, and torsional stiffness is equal to the amount of torque is required. That is the definitions. Everybody can answer, but what we observed, that sentence everybody can answer. That difference everybody can answer, but the interviewer not asking that kind of difference. What we observed from torsional rigidity and torsional stiffness, what we observed here, torsional stiffness is depends on length of the shaft, whereas in the torsional rigidity is independent on length of the shaft. Here it is independent on length of the shaft. It is independent. What does it mean is, suppose I am considering this is the shaft here. It has some length here. Length is 5 meters. Length is 5 meters. I am applying the some 10 kilonewton meter torque. Length is 5 meters. I am considering the one more shaft. The length is 10 meters, but the same amount of torque is applying on that. In such a case, the torsional rigidity is not the torsional stiffness is not constant, because here length is 5 meters, where length is 10 meters. Then if the length is increases, then the torsional stiffness is decreases, because those are inversely proportional. But the torsional rigidity is not like that, because we can look at here GJ. G is the material property, J is the cross-sectional dimensions. Here I am not changing the cross-sectional dimensions, only I am changing the length. If the length is changes, but the torsional rigidity does not change, but the torsional stiffness is changes. Okay, just we can look at this. Yes, that is the meaning of this one here. Okay, GJ divided by L, and stiffness and length is inversely proportional. Okay, inversely proportional. That is the meaning of this sentence. Torsional stiffness is depends on length of the shaft, whereas torsional rigidity is independent on length of the shaft. Finally, I conclude. Okay, that means the length is more, the stiffness is less. The short members are more stiffer than long members. Simply, not only the here, any stiffness, axial stiffness, flexural stiffness, torsional stiffness, any stiffness is depends on length. Any rigidity is independent on length here. So finally, I can give the one statement here. Short members are more stiffer than long members. Short members are more stiffer than long members. తెలుగులో ఒక సామెత ఉంటుంది, పొట్టివాడు మహా గట్టివాడు అన్నట్టుగా. Okay. Yes, this is about okay, torsion equation. Okay, how to calculate the stresses, how to calculate the okay deformation like this here, like that. Now we are going to discuss about now we are going to discuss one problem here. Please look at this problem. When subjected to a torque, a circular shaft is undergoes a twist of 1 degree in a length of 1200 meters, and maximum shear stress is induced is 80 Newton per mm square. The modulus of rigidity of the material of the shaft is 0.8 into 10 to the power of 5 Newton per mm square. What is the radius of the shaft? Okay, then what is the radius of the shaft here? Now we are going to design the shaft. How much radius we should maintain? Okay, here how much stress is developed here? 80 Newton per mm square, and the length is 1200 mm here. It undergoes to the 1 degree radian here, and that material we can look at here. Modulus of rigidity is the material 0.8 into 10 to the power of 5 Newton per mm square. Now we can look at this is the gate previous question. Option we can look at the option A 90 by pi mm, option B 108 by pi mm, option C 180 by pi, option D 216 by pi mm here. Very simple. What we are going to find out? Radius. Okay, radius we are going to find out. Then we may get a doubt here. We have the equation T by J is equal to tau by R is equal to G theta divided by the torque value. Is it given? Okay, torque value, is it given? That is a very important.
Yes, sir.
And J value, is it given? Okay, no, because in the J there is a radius here. Okay, that means we are going to find out the J value. Thereafter we can substitute here. Just we can look at here first one by one. Theta is equal to 1 degree. Okay, we can convert pi by 180 radians here. Already I told that suppose in the problem theta is given in terms of degrees, that should be converted in terms of radians here, in terms of radians. So pi by 180 radians here, and length is equal to 1200 mm here, and tau is equal to 80 Newton per mm square here. Okay, G is equal to 0.8 into 10 to the power of 5 Newton per mm square here. Then we can find out the R. How to find out? There is a one relation. Okay, tau by R is equal to, because the T value is not given, that's why I'm not considering T by J. T value is not given. Just we can look at this problem. Okay, when the shaft is subjected to torque, just mention like that. How much torque? It is not mentioned. If the torque is given, we can find out like that. Okay, it is not given. That's why we can take the relation tau by R is equal to G theta divided by L. Tau by R is equal to G theta divided by L here. Okay, from this R is equal to, can I write like this here? Tau into L divided by G theta. Tau into L. This is not T, sorry, tau. Tau into L divided by G into theta. Just we can substitute tau is equal to 80, and L is equal to 1200. G is equal to 0.8 into 10 to the power of 5, and also pi is, sorry, theta is equal to pi by 180. We can look at here, all are in terms of mm. Okay, all are in terms of mm. It is given, that's why no need to convert. So all are in terms of mm here, that's why we can convert. Okay, then answer is 216 divided by pi. Okay, just we can apply the torsion equation. But in the torsion equation, which ratio we are going to consider, that is a very important. That is depends upon the given data. We can look at here what is the data given. From that we can look at that. Okay, this is about torsion equation and analysis of the torsion equation, how to calculate the stresses and how to calculate the angle of twist. Okay, thank you. In next class we will discuss about power transmitted by the shaft and all those things here. Yes. Any doubts? Hello? Hello? Hello?
Sir.
No,
Please
sir.
respond.
No doubt, sir.
No doubts? Please ask at least one doubt. One thing you remember, your college is spending a lot of money. They are giving a lot of money. Please utilize that. We are very experts in just a few, 2 or 3 subjects only. We are not expecting on all subjects here. We have a lot of knowledge. Okay, we teach the so many students. IIT students are there in my class. NIT students are there. You can utilize. Please utilize. Every day we can answer, sir. No doubts. No doubts. No doubts. Okay. Already I told that. Don't say like that. At least we can ask one doubt. Then I can satisfy, and you are also satisfied. We have a lot of knowledge. Yes. Please ask. Please ask.
Hello.
అమ్మా ఒకటి చెప్తున్నాను, మీకు ఇంగ్లీష్ ఏమన్నా ఇన్కన్వీనియంట్ అనిపిస్తే వీ కెన్ ఆస్క్ ఇన్ తెలుగు ఆల్సో, నో ప్రాబ్లం. నేను అదే చెప్తున్నాను, మీరు దయచేసి ఇంగ్లీష్ లోనే మాట్లాడాలి. సార్కి ఏమన్నా నా ఇంగ్లీష్ అర్థమవుతుందా లేదా అవన్నీ వద్దు, మీరు దయచేసి తెలుగులో మాట్లాడండి, పర్లేదు. చెప్పండి అమ్మా, పర్లేదు. హలో 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 చెప్పండి అమ్మా, చెప్పండి అమ్మ, చెప్పండి, వినపడుతుంది. హలో హలో అమ్మ, ఒకసారి రెస్పాన్స్ ఇవ్వండి. హలో
సార్. నెట్వర్క్ ప్రాబ్లం సార్.
ఎవరికమ్మా? మీకా నాకా?
నెట్వర్క్ ప్రాబ్లం.
చెప్పండి ఇప్పుడు అర్థమవుతుంది, చెప్పండి.
టార్షన్ అనేది జస్ట్ షాఫ్ట్ లో మాత్రమే ఉంటుందా, బీమ్స్ లో కూడా ఉంటుందా?
వన్ మోర్ ఏమంటారమ్మా? షాఫ్ట్ లో ఉంటుందా? వన్ మోర్.
రెక్టాంగులర్ బీమ్స్.
రెక్టాంగులర్ బీమ్సా? నో, రెక్టాంగులర్ బీమ్స్ లో ఉండదమ్మా.
బీమ్స్ లో కూడా
నో బీమ్స్ లో ఉండదు. దయచేసి గుర్తుపెట్టుకోండి, బీమ్ డెఫినేషన్ ఏంటంటే ఇట్ ఈస్ ఎ మెంబర్ విచ్ ఈస్ సబ్జెక్టెడ్ టు ద ట్రాన్స్వర్స్ లోడ్ ఓన్లీ. ఓకే, మీరు దయచేసి ఇక్కడ చూడండి, చాలా ఇంపార్టెంట్ థింగ్. వింటున్నారా అమ్మా? వింటున్నారా? మీరు దయచేసి చూడండి, ఒక బీమ్ తీసుకోండి, ఒక రెక్టాంగులర్ బీమ్. ఆ రెక్టాంగులర్ బీమ్ లో ఒక యాక్సిస్ ఉంటుంది కదమ్మా. మీరు ట్రాన్స్ఫర్స్ లోడ్ అనేది ఆ యాక్సిస్ మీద అప్లై చేస్తే టార్షన్ ఉండదు. బట్ అదే ట్రాన్స్ఫర్స్ లోడ్ మీరు తీసుకెళ్లి ఎడ్జ్ దగ్గర అప్లై చేశారు అనుకోండి, ఎట్ ద ఎడ్జ్, దెన్ ఆటోమేటిక్ గా ఏమవుతుంది? పర్పెండిక్యులర్ డిస్టెన్స్ వస్తుంది. దెన్ ఇట్ ఈస్ సబ్జెక్టెడ్ టు ద ట్విస్టింగ్ మూమెంట్. అర్థం? కుడ్ అండర్స్టాండ్? నేను మళ్ళీ చెప్తున్నాను, బీమ్ లో మీరు లోడ్ అనేది సెంటర్ మీద యాక్ట్ చేస్తే ట్రాన్స్ఫర్స్ లోడ్ అనేది, okay, then there is no twisting moment. The same load we can apply at the edge of the beam, then there is a twisting moment. Otherwise there is no twisting moment. అలాగా లోడ్ అప్లై చేస్తే దాన్ని మనం సింపుల్ గా బీమ్ అనడానికి లేదు. ద బీమ్ ఈజ్ సబ్జెక్టెడ్ టు ద ట్విస్టింగ్ మూమెంట్, బెండింగ్ మూమెంట్, షియర్ ఫోర్స్ అని 3 నేమ్స్ ఇవ్వాలి. ఓకే, సింపుల్ గా బీమ్ డెఫినేషన్ ఏంటంటే, ఇట్ ఈస్ ఎ మెంబర్ విచ్ ఈస్ సబ్జెక్టెడ్ టు ద ట్రాన్స్వర్స్ లోడ్ విచ్ ఈస్ యాక్టింగ్ ఎట్ ఎ center line, not at the edges. Okay, is it clear?
Yes, sir.
Hello?
Yes, sir.
Any doubts? Very good doubt. Any doubts? మీరు దయచేసి అట్లీస్ట్ 1 డౌట్ అని అడగాలి. చెప్పండి అమ్మా, పర్లేదు. హలో, నో డౌట్స్? Okay, can I wind up the class? Hello?
Sir, could you please send me this
ఎస్ సార్.
PDF to the group?
In the video?
No, sir. The slides, please send to the group, sir.
Yes. I will send to the group here. Actually, I have the all PDFs here. But నేను ఏం చేస్తున్నానంటే అన్ని పీడిఎఫ్లు ప్రీవియస్గా ఏంటంటే ఆల్ టాపిక్స్ ఒకే పీడిఎఫ్ పెట్టానమ్మా. ఇప్పుడు చేంజ్ చేస్తున్నాను, అన్ని నేమ్స్ వైజ్ చేంజ్ చేసేసి మీకు కంపల్సరీ సెండ్ చేస్తానమ్మా. ఓకే, అవును. నేను ఎందుకు సెండ్ చేయలేదంటే ఈచ్ అండ్ ఎవ్రీ టాపిక్ సపరేట్ చేసి సెండ్ చేద్దాం అనుకుంటా. నేను కంపల్సరీ సెండ్ చేస్తాను. టుమారో కంపల్సరీ సెండ్ చేస్తాను. ఓకేనమ్మా?
Okay, sir. Thank you. Okay, sir.
ఓకే అమ్మా, థ్యాంక్ యూ వెరీ
Okay,
మచ్.
sir.
థ్యాంక్ యూ.
Thank you, sir.
ఓకే,
Thank you
ఓకే,
so much.
ఓకే.
Thank you, sir.
థ్యాంక్ యూ.